Welcome to the rest of the lecture notes for section 1.5. I'm going to quickly go through this and do some examples so you're able to see how all of the transformations go together. We stopped in class right here at the horizontal shift to left and right. Quick reminder, horizontal shift is the exact opposite of what you see here. And we'll talk more about why in class this is true, but just remember that for now, anything that's inside touching the x is intuitively exactly opposite of what you would notice. For example, this is plus, and you'd want it to go to the right, but this actual transformation is 3 to the left, as we were talking about in last class. So I added the graph that was the original red function here. It was moved to the right too. I also symbolically added f of x equals x squared and gave you the verbal part, the square function. I think now would be a really good time to look at an example. The example I want to look at is A on this sheet of paper. I have a horizontal shift and I have a vertical shift inside the function g of t. G of t, the parent function, is f of x equals x squared, and I got that from this symbol over here, the squared. I can see that something is touching the t. That's going to be a horizontal shift right 1 unit. And this piece, this 3 piece, is going to be a vertical shift up 3 units. An easy way of doing these shifts is to put the original parent function on your piece of paper. And that's why 1.4 asked you to really look at the parent functions and the library of functions, so you can easily graph this parent function as 0, 0, negative 1, 1, 1, 1, 2, 4, and 3, 9. Let me use symmetry really quick. Here's your original function. But each of these ordered pairs has been moved and shifted left, right, and up and down. Specifically, right 1 and up 3. And it doesn't matter what order you do this, you're going to get the same graph. So take this point 0, 0 and move it right 1 and up 1, 2, 3. There's your new vertex. Take this point and move it right 1 and up 1, 2, 3. And there's its new point. Take negative 1, 1, move it right 1 and up 1, 2, 3. There's your new point. Take the point 2, 4, which is here, move it right 1 and up 1, 2, 3. Take the ordered pair negative 2, 4, move it right 1 and up 1, 2, 3. Take the ordered pair negative 3, 9 and move it right 1 and up 1, 2, 3. Take the ordered pair 3, 9 and move it right 1 and up 1, 2, 3. And here is your new parabola under that transformation. You'll notice that these transformations can be done more than one at a time. And that's what this example shows. We're going to come back to this example worksheet after every couple parts of the lecture notes, so you get some practice seeing what this looks like. So back to the lecture notes. Our next transformations are reflections over the x-axis and reflections over the y-axis. I'm going to zoom in here so you can see it, and then I'll zoom out just a little bit. So the square root graph is our parent function. Symbolically, that's f of x equals x square root x, and its square root function. Here's its original table. We saw that from a couple pages ago. Here's its original graph. This graph says, change the sign of all my x values. Okay, well here are my x values. 0 actually doesn't change sign, but 1 becomes negative 1, 4 becomes negative 4, 9 becomes negative 9, 16 becomes negative 16, and leave all my y values alone because there's nothing here affecting the y values. When I graph that, 0, 0 doesn't change, negative 1, 1 goes here, negative 4, 2 goes here, and I don't have the 9, 3 on there, so I just have to remember the shape of it kind of going this way. And you can take a look. If this is the y-axis, this function has been reflected over the y-axis. So I'm going to write that down here. This function's been reflected over y-axis. F of negative x looks like this, symbolically. And I didn't tell you what to do. Here you change the signs of the x's. However, that's not what this table is asking you to do. This third table is asking you to change the sign of the y values. So I'm just going to write the x values from the original table, and I'm going to change all the signs of the y values, and I'm going to graph. When I do that, I've got 0, 0. I have positive 1, negative 1, positive 4, negative 2, and then, of course, the 9 isn't on there, so I'm going to go ahead and connect. And if you'll notice, this reflected it over the x-axis. I'm going to actually write axis. There we go. Symbolically, negative f of x looks like a negative sign and then the square root x. Notice the negative sign is inside with the x when I need to reflect over the y-axis, and outside of the square root when I need to reflect over the x-axis. Again, we're changing the signs of the y's to obtain a graph that's reflected over the x-axis. So to practice that, I have an example here of the square root function that has a negative sign outside the square root and a negative sign inside the square root. The negative sign on the outside of the square root tells me to reflect over x. The negative sign on the on the inside is telling me to reflect over y-axis. So take my original function, 0, 0, 1, 1, 1, 2, 3, 4, 2. I'm going to go ahead and graph this. And each and every ordered pair is going to be reflected over the x-axis and then reflected over the y-axis. These reflections can be done in any order. So I'm going to start with x-axis and then go to y-axis. The point 0, 0 is boring. It literally reflects over the x and y and stays the same. But 1, 1 reflected over the x-axis puts it down here. Reflected over the y-axis puts it over here. Again, reflecting over the x-axis changed the sign of the y. Reflecting over the y-axis changes the sign of the x-axis, the sign of the x value. This point 4, 2, reflecting over the x-axis puts it down here at 4, negative 2. Reflecting over the y-axis puts it over at negative 4, negative 2, which is right here. And then continuing that, this is the function negative root negative x. This is the function square root of x. So this has undergone 2 transformations. It's kind of cool. Moving on. I'm still going to play around with the square root function, except I'm going to vertically compress and stretch. Compressing is making it smaller. And stretching is making it longer this way, on the x-axis going this way. So if I want to vertically manipulate something, it needs to be on the outside of the y value, just as this notation is telling us. Literally, this notation is saying, take your y value and multiply it by 2. So 0 times 2 is just 0. 2 times 1 is just 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. I'm going to go ahead and graph that on the axis with the original parent function. So it's going to be 0, 0, 1 is no longer going to be going to 1. 1 is going to be going to 2. 4 is no longer going to go to 2. It's going to go to 4. 1, 2, 3, 4. And then 9, if I could graph it, would have gone to 6. So it's going to look like that. Same shape as the square root, but it's vertically getting stretched. So the function notation is 2 times the original function, which is 2 times the square root of x. So anytime you've got a number on the outside of the root, you know you've done something to it vertically. 2 times f of x equals 2 times the square root of x. When I say this verbally, it is vertically stretch by a factor of 2. I'll show that down. Vertically stretch by a factor of 2. Symbolically, by the way, the original function is the square root of x. Now I'd like to show a vertical compression, and it's not a coincidence that this number is a fraction. All compressions are fractions. So I'm going to write this first. Vertically compress by a factor of 1/2. Anytime you've identified your factor as a fraction, that means that whatever transformation you're doing is going to be a compression. That's going to come into a large play next transformation. But for now, I just want you to know that anytime you've got a fraction here, it means this word should be compressed. Symbolically, it would be 1/2 of all your f of x, which would be 1/2, and your f of x in this case is the square root of x. So it would be 1/2 of the square root of x. Working our way back up, this literally says, take your y value and multiply it by 1/2. Multiplying by 1/2 is literally the same as dividing by 2. For those that are like, why don't you just say divide by 2? I could have. 0 divided by 2 is just 0. 1 divided by 2 is 1/2. 2 divided by 2 is 1. 3 divided by 2 is 3/2. 4 divided by 2 is just 2. Graphing that on the same axis as the parent function, 0, 0. 1, 1/2, you're going to have to approximate. 4, 1, here. And if I could do 9, 7, 8, 9, it would have been 3/2, which is right around here. And there you go. I have vertically compressed this to get the blue function. So these are vertical stretches and compressions, and the numbers are always on the outside of the f of x, meaning they're always right in front, multiplied by them. So let's go to horizontal compressions and stretches. And I want to remind everyone here that if it is touching the x, it is the exact opposite of what you would expect. You have 3 times x here. The inverse of multiplication is division. So really what you're doing is taking your x value and you can either say divide by 3 or multiply by 1/3. Again, I left my y values alone. My original table is going to be the square root table. I left just these 2 pieces down here to remind you that you can always extend this table if you need to. So here is the extended table. I need to take my original x value and multiply it by 1/3, which is the same as dividing by 3. 0 divided by 3 is 0. 1 divided by 3 is 1/3. 4 times 1/3, or 4 divided by 3, is 4/3. 9 times 1/3, or 9 divided by 3, is just 3. 16 divided by 3 is 16/3. 25 divided by 3 is 25/3. 36 divided by 3 is 12. So I've taken all of my x values and multiplied them by 1/3. When I graph that, 0, 0, doesn't really go anywhere. 1/3 is kind of difficult to graph, but I'm going to eyeball it there. 4/3, 2. So 4/3 is 1 and 1/3 more, which is right around here, and it's now 2. I'm going to come back here and say that this should have been 1/3 1, not 1 1/3. 1/3 1 is here. So for those that caught that, nice job, I just caught it. I need to do the next, which is 3 3. So 1 2 3, 1 2 3. 16/3. So again, 15/3 would be 5, so it would be 5 and 1/3, which is right around here, and then the number 4. 25/3, you can convert to 24/3, which is 8 and 1/3. So do I have an 8 on here? 6, 7, 8, and a little bit longer is 1/3 and make that 5. And here is your new graph. When you do this, you are compressing vertically. You are literally being able to write more x values when you were only originally able to write a couple. And again, I will explore this so much more in detail in class, but I wanted you to get this first look at it. So symbolically, this is f of x equals root x. I hope you see that this is the square root function. I've used it a lot in these notes. This function notation, everywhere I see an x, replace it with 3x. And it is a horizontal compression by a factor of 3. On this bottom part here, it literally says everything I'm going to reiterate in class 10 times. Everything that affects the x value exactly the opposite of what your intuition is telling you. So when I apply that knowledge to this next example, I have 1/2 of an x. The inverse of 1/2 is multiply it by 2. So this right here is take your x value and multiply it by 2. So my original x value here is 0. 0 times 2 is 0. 1 times 2 is 2. 2 times 4 is 8. 9 times 2 is 18. 16 times 2 is 32. 25 times 2 is 50. 36 times 2 is 72. And honestly, we're not going to be able to graph any of these because they don't appear on our graph. But I'd like you to notice that in my original graph, I could graph 4, 2. But in my horizontally stretched graph, I have to now put that same y value on 8, which is way further away than it originally was, which is why we call this a horizontal stretch, because I'm taking 4, 2 and I'm stretching it to the x value of 8. That looks like 0, 0, 2, 1, and 8, 2. When I connect it, it looks like that. Function notationally, this becomes f of 1/2 of an x, which is the square root of 1/2 x. Replace all x's with 1/2 x. This is a horizontal stretch by a factor of 2. Reminding you that these two pieces are linked. Take x values and multiply them by 2 is literally linked with by a factor of 2. These numbers, whatever you're doing to the x, should be the same here. Quick reminder again, if this number is a 2, you've got a stretch. I know it's deceiving because you want to say this is a compression because this is a fraction, but I want to remind you this fraction becomes the 2 because the inverse of 1 divided by 2 is 2 over 1. Doing this example might make it a little bit easier to see. I'm going to zoom in on this example. These aren't part of your notes, but I just thought it would be nice to just see an example like right in the moment. This 3 is a vertical stretch by a factor of 3. So take all my y values and multiply them by 3. However, this 2 is inside the absolute value touching the input of d, so it's the exact inverse of this particular operation, so it would be 2 times d becomes 1/2. Because this is a 1/2, it's a horizontal compression by a factor of 1/2. So what does that mean? Well, I'm going to go ahead and graph the original function. The absolute value was 0, 0, 1, 1, negative 1, 1, and then the linear lines that go both sides. I'm going to take a straight edge and graph that so you can see the original function and how it's being affected by both of these two stretches and compressions. There's my original. And I take this ordered pair by ordered pair. What I mean by that is I'm going to start with 0, 0. I'm going to take the original ordered pair, 0, 0. Just to be a little bit more clear, I'm going to take your original 0, 0. And it doesn't matter what order you do these two in, if it's just compressions and stretches together. So I'm just going to take the vertical stretch first. I'm going to take the y value and I'm going to multiply it by 3. The y value multiplied by 3, well, this is boring. 0 times 3 is just 0. I'm going to take the original x value and multiply it by 1/2, and that's just 0, which again is not very interesting. And there's my new ordered pair. It came from the vertical stretch that multiplied the y value by 3, and the horizontal stretch that multiplied the x value by 1/2. And my new point is 0, 0. Put that in purple, because color matters. So our next ordered pair is 1, 1. That's from the original. If I'm going to take this in 2 steps, the very first step is what is going on with the y value. I'm multiplying the y value by 3, so that gets me this. 1 times 3 is 3. I'm multiplying the original x value by 1/2, so this becomes the new ordered pair, 1/2 comma 3, which is go over 1/2, 1, 2, 3. Here's my new point. I'm going to take a random ordered pair from the other side of the absolute value. I'm going to take 4, 4. And I'm going to do exactly what I've been doing before. Take the y value and multiply it by 3 to get 12. Take the x value and multiply it by 1/2 to get 2. And the original ordered pair 4, 4 has now been horizontally compressed, so it's gone closer to the y-axis by 1/2, so that would be going half the distance here, and then amplified up 12, so this would be 4, 5, 6, 7, 8, 9, 10, 11, 12, so it now would look right up here. So remember, I've got 0, 0, I've got this one and that one. You are welcome to take more of these ordered pairs and run them through multiplying the y value by 3 and the x value by 1/2, but I have enough information with 2 ordered pairs to draw this graph, as long as I'm really careful. So the original function is this wide V. You'll notice this V under the horizontal compression and vertical stretch. It's really getting much, much closer to the y-axis. So, to review, we've got shifting left and right, up and down. We've got reflecting over x and reflecting over y. And now we have vertical stretches and compressions. And those are all of the possible transformations that you can do to a function. And linking this to kind of a graphic. And I'm sorry that this graphic has a lot of color, but I just went a little crazy on the color. When you take a look at these original functions, you have some kind of f of x. If there is a negative sign here, that means you have flipped it over the x-axis. If you have a number here, it's because you've vertically stretched or compressed it. If you have a negative sign here, it's because you reflected it over the y-axis. If you have a number that's multiplied by the x, it's because you've horizontally stretched or compressed it. If you have a number that is adding and subtracting the x, it's because you've shifted left or shifted right. If you have a number that is affecting the y values on the outside, it's because you shifted vertically up or down. I'm going to go over this in class, but I wanted to have a very firm, hey, this can be, I guess, memorized, which makes you feel uncomfortable, but this can be looked at as where are the numbers going on your function. It matters what order you do transformation. Just like order of operations, you do multiplication before addition. Reflecting over x and y is like multiplying by -1. So all your reflections go first. And for those that can't read that, that says reflection over x and or y axis. After you've done the reflections, if they're there, then you need to do all the stretches and compressions. And these, it doesn't matter if you do the vertical compression stretch first or the horizontal compression stretch first, but you must do reflections first, then all the stretches and compressions. Only after you're done with the multiplication can you do the adding and subtraction, which are your horizontal and vertical shifts, left, right, and or up, down. Quick reminder, if all you have of your transformations is shifts, it doesn't matter what you do, what order you do them in. But any time you add one of these others included, it means, wait a minute, you've got to follow this order. I'd like to do an example, a rather complicated example, but I'd like to do an example for you now, just so you know, like, hey, this is what she's talking about. I'd like to do this from the Transformations Practice worksheet, which I am including in the second email of this week. You can download this and print it, and I will have copies for you in the classroom when you come back to class next week. So you'll notice I have not at all identified the parent function here. I'm just giving this to you in function notation. I'm asking, what transformations did you do to this function, even though you don't even know what the function is? So taking a look at the notes, I have a 3 times y values. A 3 times y values are vertical stretch by a factor of 3. I'm starting to lose my voice, so I'm sorry. That's starting to be raspy. That's the 3. The x minus 4 is a horizontal shift right 4 units. I have to stop and ask myself, did I put this in the appropriate order? I think I did, because I made sure that anything that was multiplication, like this 3, was written first, and anything that was addition and subtraction was written second. I'd like to skip to D. We're going to do C, E, B in class, but D I'd like to talk about because it includes something funky inside. So for D, I have 3 or 4 transformations that I can see. I have a negative sign, which means I've got some kind of reflection. Oops, the lights just went out. If you'll give me a second, I'm going to put the lights back on. While the lights come on, I'm going to put the lamp on the document camera. I apologize. Okay, cool. All right, sorry about that. It was unexpected. So I've got a negative sign here, which means I've got some kind of reflection I've got a 1/5 here, and I know that's on the outside, it's not touching the axis, so I know that's a vertical stretch or compression. Because it's a fraction, I know it's a compression. I've got 2 times x right here, so I've got to figure out what that has to be, and I have a +4 inside with the x. Students everywhere look at this and say, well, Amy, that means go to the left 4. But I want to remind you that this needs to be factored because you can need to take the 2 off the x. X needs to be by itself all the time. So what should have been written here is -1/5, that doesn't change, but inside this piece you need to factor the 2 out of both pieces of the domain. So it would be 2 times x, so now x is by itself, plus 2. And now let's break this apart. We need to remind ourselves that the appropriate order is reflections, stretches and compressions, then shifts left and right. So in the appropriate order, I'm going to start with the purple negative sign. That is a reflection over the x-axis. There's our first one. I don't have any more reflections because I have no more negative signs, so I'm done with all my reflections, and I can move on to stretches and compressions. The first stretch and compression I see when I'm moving through this is 1/5, but there is another one inside with the x. So I can say that this 1/5 is affecting the y value, so that's vertical, and this 2 is affecting the x values because it's inside with the domain, and that's going to be a horizontal. So it doesn't matter what order you do them once you identify them as compressions and stretches. So I'm going to say that the first one is a vertical compression by a factor of 1/5. And because it's touching the y, I don't have to do any work. It's exactly the way it is. But because this is touching the x, I have to do the inverse of what I see. This is 2 times this thing, so I need to do this piece divided by 2. So this becomes a horizontal, and I'm going to leave this blank, but I know it's by a factor of 1/2. Now, because this is a fraction, that means the word you need to write here is compression. That's kind of how I easily work my way through these. So now I've got reflections, stretches and compressions, and now I have one more transformation left, and that is going to be my shift. And because it's touching the x's, it is a horizontal shift. So this is a horizontal shift left 2 units. And here are all the transformations when I'm given function notation in the appropriate order. I think this is a good place to stop, simply because I think you've got a really great foundation. I'm not asking you to do any of the homework from this particular unit yet, or this particular section yet. Instead, if you are in my Monday, Wednesday class, I want you to download and print this worksheet and just start doing the problems. It's not due, but we're going to discuss them, and I would like to see how you went without any assistance. You don't have to go to the tutoring center, you don't have to come to an office hour, but I would like you to go through and say, okay, I was able to do example 0, I was able to do example 1, I was able to do example 2, or I wasn't. Having the information that you can and cannot do, if you take a look at example 4, these 2 right here, don't do them. Don't even bother doing them right now. But I'm hoping you're able to do these as a review. Here's another one that looks like example 0, so it gives you another chance to take a look at a bunch of transformations. And the follow-up is, do you know what each of these transformations does to the ordered pair x and y? And if you're wondering, hey Amy, where did that come from? Well, I went through the notes here and I literally told you what to do to the x's and y's for each of the appropriate transformations. If you're my Monday, Wednesday class or my Tuesday, Thursday class, quick reminder that the lecture notes for next week should appear sometime this weekend, so make sure to download those and print them if they're helpful to you. And that I wanted to close with one example, last one. To graph this, I'm going to identify the parent function as f of x equals x cubed. That looks like this. 1, 1, negative 1, 1, 2, 8. And then negative 2, 8. I should have a scale on here, so when you see these in class, I will add the scale in. It originally looked something like this. I'm just going to kind of list the ordered pairs here. So I'm like going to go negative 2, negative 8, negative 1, 0, 0, 1, 1, and 2, 8. Those are the quick ordered pairs from the x cubed graph. And now I'm going to start listing the transformations in order. But before I do, I notice I have this negative 2 in here and here, so I'm going to go ahead and inside the x, factor it out. And when I do, I take it out of this to get negative 2, and I take negative 4 and divide it by 2 to get positive 2. And now I can finally list the transformations. I do have one negative sign. It's inside the x, so it is a reflect over y-axis, or change the sign of all my x values. Quick reminder. The next is this multiplication 2, because the other two transformations are not multiplication. So that would be a horizontal, because it's touching the x, and I'm going to leave it blank, by a factor of, because it's touching the x, it's the exact inverse of what's sitting here. It's 2 times x, so I'm going to take this x and divide it by 2, which is written 1/2. Because this is a fraction, you need to write compression. Oh, I'm sorry, I got those right in the wrong place. Nice job, Amy. So that would be compression by a factor of 1/2, which means takes all my x values after I've done the reflection, multiply them by 1/2, or divide them by 2. I have 2 more transformations. I have horizontally, shift, and in this case, it's going to be left 2, because it's opposite of what you see. And this one is the last transformation, which is vertically, shift, up 3 units. So, quick reminder, reflect over y-axis means change the signs of all my x values, so I'm going to do that first. Horizontal compressed by a factor of 1/2 means take all my x values and multiply them by 1/2, so that's what I'm going to do. Horizontally shift left 2, so if I'm going to go left, I'm going to go subtract 2 from each of my x values. If I'm going to go up, I'm going to add 3 to my y values. So let's do that to these ordered pairs and then graph. This is the way I graph. You don't have to do it this way. Some people are so amazing artistically and spatially, they can literally do this on the graph. I think you know I am not artistic or spatially exceptional, so I have to do this little by little. And it looks like this. I need to first reflect over the y-axis, which means change all the sign of the x values. So this negative 2 is now 2, 8. This negative 1 is 1, negative 1, 0, 0. Well, that's boring. And you'll notice all I'm doing is changing the sign of my x value. Okay, so I've done all the reflect over the y-axis. That's what I just checked off. I'm going on to the next one, which is horizontal compression by a factor of 1/2, which means take all of my now new x values after the reflection and multiply them by 1/2. So 2 times 1/2 is 2 divided by 2, or 1. Leave the y value alone. 1 times 1/2, or 1 divided by 2, is 1/2, comma negative 1. Okay, 0, 0. I've got to multiply it by 1/2, it just stays 0, 0. Negative 1 times 1/2 is negative 1/2. leave the y value alone. Negative 2 times 1/2, negative 1, leave the y value alone. And now I've done all my horizontal compression. Next, I'm going to do shift left 2, which is subtract 2 from all of my x values. 1 minus 2 is negative 1, leave the y value alone. 1/2 minus 2. So you can do this on the graph if you wish. This is 1/2 minus 2 would be 1, 2, or negative 3/2. Otherwise, you would just do the arithmetic, 2 minus 1/2. Leave the y value alone. Nice thing here is, finally, my 0, 0 moves. It just happens to need to move left 2, so take 0 and subtract 2 to get negative 2, 0. Negative 1/2 minus 1/2, or negative 1/2 minus 2. For those that need to see this, negative 1/2 minus 2 is the same as negative 1/2 minus 4/2 to get negative 5/2. Leave the y value alone. Negative 1 minus 2 is negative 3. Leave the y value alone. And last but not least, now that we've done our horizontal shift all the way down, is going to be my vertical shift up 3, which takes all my y values, leaving these x values alone. I'm just going to look at these y values and add 3. Negative 1, 3 plus 8 is 11. Negative 3/2, negative 1 plus 3 is 2. Okay, negative 2, 0 plus 3 is 3. Negative 5/2 stays, not touching it, but I'm adding 3 to 1 to get 4. Negative 3 stays, I'm adding 3 to 8 to get 11. And I'm going to graph all of these points. And if it looks like this shape, mostly, with maybe some horizontal compression and moving left, right, up, and reflecting, then I'm good. But if it starts looking bizarro, something's wrong in this particular thread. And that means I need to go back and take a look. So let's hold our breath and hope it's great. So we've got negative 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's my new point, and it literally came from negative 2, negative 8. I'm just going to tidy it up every time I point something. Negative 3/2 is the same as negative 1 and 1/2, 2. Goes right here. Negative 2, 3 is here. Negative 5/2 is negative 2.5, 4. Negative 3, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's right here. And here's the moment of truth. When I connect these beautiful pieces, does it appear that it has been reflected over the y-axis, squished together horizontally, then shifted left 2 and up 3? And it is. So I hope that was helpful, and if it wasn't helpful, I hope you give me some feedback, and we will reconvene Monday, Wednesday on Wednesday, and your notes need to be done. And again, Monday, Wednesday students, you need to attempt these problems on the worksheet that I'm handing you, or I'm attaching to this email. Tuesday, Thursday, you do not need to do that. Tuesday, Thursday, only do this transformation practice if you wish, and I will see you next week.